Hello and welcome. This video is for sections 11.1, 11.2. The main learning objectives are to determine whether we can refute a given claim of expected frequencies, and also to determine whether the two categorical variables in a contingency table are independent. With that, let's just get going on some examples so you can start seeing what this is, and I can make some definitions and explain a little bit about the procedure. Okay, so our first objective is to determine whether we can refute a given claim of expected frequencies. Frequencies or probabilities or how often something happens, you have lots of experience with. If you have knowledge of like games of chance, the roulette wheel has a certain chance to land on a number, and you have a certain chance of showing up to work or whatever. There's all kinds of different chances or frequencies, and we have expected frequencies or expected chances. And we can use a sample of data to see if we can reject the expected frequencies or whether we do not have enough evidence to reject the expected frequencies. So the example I have here is that we have a claim that the frequency of LMC employee sick days is the same regardless of the day of the week. So Monday, Tuesday, Wednesday, Thursday, Friday, 5 days of the week. And the claim is that the frequency of sick days is the same for each of those 5 days. 100% divided by 5 is 20%. So our claimed frequency, our expected frequency is 20% for each day across the board. Notice that those five add up to 100%, just like any kind of probability distribution. The sum of all the frequencies has to add to 100%. And also, just as we've done throughout the semester, we're going to use the frequencies of a sample of the population to determine if we have enough evidence to refute the claim. All right, so we're going to perform a little hypothesis test here. Our null hypothesis are the frequency R as claimed. So in this case, 20% for every day. And the alternative hypothesis is that at least one of the claimed frequencies is incorrect. So this is very standard in terms of our null hypothesis and alternative hypotheses. The frequencies are as expected, or the frequencies are as claimed. And then the alternative is at least one of the frequencies are not as expected or claimed. We're going to test this at the 5% level. And to do that, we need a sample of the data. So I have here a sample of data. I took an SRS of 100 LMC employee absences and recorded the days in which those absences occurred. There are 116 absences that occurred on Monday of the 500 absences that were randomly selected. And the counts here are listed in the table. Just as a note, there are requirements for every formula to be correct in statistics. We just can't use formulas whenever we feel like it. There are requirements for when the formulas actually give you reasonably correct answers. For a fit for the claimed frequencies, the requirements are we need a simple random sample and that each category has an expected count of at least 5. Now, all these counts here for Monday through Friday have counts that are at least 5, but please note that it doesn't say that the sample counts are at least 5. It says the expected counts are at least 5. So what's the difference there? Well, we are expecting, according to the null hypothesis, that 20% occur on Monday and 20% occur on every single other day. So if this null hypothesis were correct, then we expect 20% of the absences to be on a Monday. There are 500 data items. So you take the 500 data items, you multiply by the 20%, and 20% of 500 is 100. So this is the expected count. And that's the same for each day because each day happens to have the same frequency claim. So the expected count for each one is 100, which is definitely more than 5. So we don't actually need the counts to be more than 5. We need the expected counts to be more than 5, or at least 5. All right, so now we're going to use our statistics formulas because we have an SRS, we have expected counts of at least 5, and we can use our statistics to calculate our p-value, our test statistic, etc., to determine whether we have enough evidence to reject the null hypothesis. So we need to tell our software this data. So I have already put that data into StatCrunch. So by the way, for StatCrunch and a lot of other basic spreadsheet formulas, you'll need to do these in columns. So for the worksheet, they were listed horizontally Monday, Tuesday, Wednesday, Thursday, Friday. But oftentimes when you're doing things with technology, you have to list them vertically so that they can spot the columns. So I just transferred all this information over there. I'm going to go to stat, and the selection of whether or not the frequencies are as expected is called goodness of fit. And we're going to use a chi-squared test. That's the standard goodness of fit test. We're trying to see if the sample frequencies fit the expected frequencies. So I go to a chi-square test. The observed, well, that's the sample counts right here. That's what we observed. And the expected, here is the expected frequency. Whoops. The expected frequency or the frequency that we're claiming here is 20%, 20%, 20%, and I would put that in the expected frequency thing here. Because these are all the same, 20, 20, 20, 20, 20%, we can actually select this one and say that they're all equal. So we can do either one in this situation because they are all equal, or we can just select the column and say that the expected frequency is where we have these claims here. All right, and then we're going to hit compute, and we get a little outcome box here, and it says here that we had 500 items. The degrees of frequency are 4 because there are 4 different sort of categories: Monday, Tuesday, Wednesday, Thursday, Friday, and n-1 would be the degrees of freedom. So we have 4 degrees of freedom. The chi-squared test statistic is 6.14, and the p-value is 0.11 or 1889. If it does ask you for the critical value, it will give you a table. So I have here an example of our homework here. And whoops, looks like I need to pause and reload it in. Give me 1 sec. Whoops. That was pausing the screen, not pausing the video. Okay, I got this. I got this. Don't worry. And I'm back. Okay, so I just went to my stat lab and went to our homework assignment, and I just picked a question randomly, like number 11, and it does allow, it has a little pop-up for the critical values. So I just typed it here, chi-square distribution table. It gives you the critical value. You have to know the degrees of freedom. Remember, it was 4 degrees of freedom, and we're testing at the 5% significance level. So there's the 4, and I have to go all the way over here to 5%. Oops, that's 0.05. There's 0.05 is 5%. So it's the 4th one down, just letting you know, like 1, 2, 3, 4. So it's the 4th one down. So I need to go 1, 2, 3, 4. So 9.488 would be the critical value. So if it asks you for critical values, you just pop up the little table and you read off the number that's appropriate for whatever you're given in terms of degrees of freedom and your significance level. Okay, so there's the 9.488 value that I just looked up right there. So that doesn't come from StatCrunch directly. You have to look it up or do a formula to get it. So we have 2 different methods for determining whether a hypothesis test has enough evidence to refute the null hypothesis or not. And the 2 methods, of course, are the test statistic method and the p-value method. We've been doing these pretty much all semester. I personally prefer the p-value method, but if you prefer the test statistic method, fantastic, you can use that. They do ask you to use one or the other at times during the homework, so you have at least an ability to use either method. So for the test statistic method, you get your test statistic, which was the chi-squared number, which was 6.14. That was from the little pop-up I got here. 6.14 was the chi-squared number here. And the p-value is 0.1889. So I just transfer that information over here. So 6.14, if the test statistic is smaller than the critical value, then if the test statistic is smaller than the critical value, in other words, if we don't have a larger test statistic than the critical value, then we don't have enough evidence to reject. Just like if the p-value is not smaller than the significance level, we don't have enough evidence to reject, right? If a p is very small, then we can reject the null hypothesis. And if the test statistic is very large, we can reject the null hypothesis. And we get the same result both times. Just we do have the p-value smaller. I mean, not smaller. Why do I say this backwards? The p-value is larger than 0.05, right? So it's not smaller, right? And the test statistic is smaller, it's not larger, right? It's backwards from each other. That's why I'm getting tripped up over my own words. In any case, whichever method you use, if you do it correctly and don't trip over your words as much as me, you will know that we do not have enough evidence at this 5% significance level to reject the claim, the null hypothesis. In other words, we cannot reject the claim that the frequencies is the same. In other words, we don't have enough evidence to say that they're not the same every day. So even though it looked like Monday had a lot more than maybe Thursday, and even Friday had a bunch, it wasn't significantly much, right? So you flip a coin 10 times, you get 7 heads. Is that a significant number of heads out of 10 to say that the coin is a cheat, that it's like weighted or like somehow not true? Probably not, right? So even though you get a majority in one category, it may not be enough evidence to say that we can reject the null hypothesis. And that's the situation here, right? We don't have enough evidence to reject the claim that the 6 days sick days are the same pretty much every day of the week. All right, so that's how we do our first objective. That's how we determine if a bunch of claimed frequencies can be refuted or not. Our second objective talks about a contingency table and whether we can determine whether the categorical variables are independent or not. Let me first start by just defining and reviewing some vocabulary words. So contingency table, although you may not have heard of it, we did talk about a little bit, or maybe you don't remember it, but we did talk about it a little bit earlier in the course. But I'll just remind you and go over exactly what it is. It shows the relative counts between two categorical variables. And so anytime we have, kind of things like, who likes pizza and, who wants to go to the movie, that's two categorical variables, and they can have some overlap or not. And so the relative counts of those put into a table is called a contingency table. A contingency table is sometimes called a two-way table because you have a horizontal and a vertical. The horizontal is one of the categorical variables, and the vertical is the other of the categorical variables. And every time you have a cell where they intersect, is going to be a count for what they have in common for that. So I have a also reminder of what independent and dependent means. So we say that variables are independent. We say they're independent. That means that when choosing a data item from one variable, it does not affect the data from the other variable. So my example here was a student's favorite color is likely to be independent of their academic major, right? So what they major in college probably is independent from their favorite color. Maybe not, but I would guess that it is. It seems like it's probably independent because we can't imagine any reason why they would be dependent. By the way, we could use this test. We could take some data and use this test to see if we could refute the independence claim. Okay, so let me go on to the other definition, which is dependent. So dependent. So variables are dependent. That means that when choosing a data item from one variable, it will affect the likelihood of some of the data from the other variable. And my example here is a person's highest level of education completed is likely to have a dependent relationship with their income tax bracket. Now, not always, certainly it won't be always one affects the other, but we can definitely see that it's possible that your highest level of education will have some impact on your income tax bracket, or vice versa, right? So those seem like they are probably dependent upon each other. So that's just trying to help you understand and remember what these different words mean. Let's jump into an example so I can show you how this actually works, actually with numbers and stuff. All right, so I have here a contingency table. I'm going to zoom a little bit to make it a little easier for people to read on their screen. And so there's a question I have, for example, two, considering medical treatments for foot ailments, does the likelihood of success or failure depend on the type of treatment used? Are there some treatments that are better? In other words, is the success or failure independent of the type of treatment, or does it depend on the type of treatment? So that's what we're trying to see, if they're independent or dependent. So I have my little table here. It's a contingency table summarizing the results of different foot procedures and the relative success and failure of each. So this is a little sample that we have here. And so foot surgery, 54 successes, 12 failures, etc. So we have all these counts for the two categorical variables. The vertical variable is the type of procedure, and the horizontal variable is success or failure. And each time we have an intersection, we could read off the successes for a burglary or the failures for weight-bearing casts, etc. So that's how a contingency table is organized. All right, so we're going to test to see whether these two variables are independent, or whether, well, we're going to test whether we can refute whether the two variables are independent. We can never really prove they're independent, just that we have enough evidence or don't have enough evidence to refute the claim of independence. And I'll just go over again the requirements for us to use our statistics. We need a simple random sample, and every cell in this table, which means every number listed, has to have an expected count of at least 5. The data I got this from, it didn't say it was a simple random sample, but for the purposes of this video, just to kind of go with explanation of how it works, let's assume that they got this from a simple random sample. And then again, I'll talk about the expected count of at least 5. Some of you sharp-eyed viewers may have noticed that we have a count of 3 over here. And that is mathematically smaller than 5, right? So that on its face may sound like it violates this Part B requirement that the expected count is at least 5. Remember, this is the expected count, not the sample count. So if we would have an equal, frequency of success and failure, means half the time it's success, half the time it's failure. We have in this, at least in this one row right here, 70 successes and 3 failures. If they were equally likely, I guess we can't really do it that way, but you can see it that way. But let's look at it another way. That's just the proper way. If you look at success failure on each of these things, right? If you look at success failure in each of these things, you will notice that if they were the same for each of these, we would have something like, here's 5 times as many or 4 times as many successes as failures, about the same number of successes as failures, 3 times the number of successes as failures. We would have something like 3 or 4 or 5 or 1. We would have the same sort of ratio of successes and failures for this 3. So if we had a similar ratio or expected number of failures, it would not be 70 to 3, which is like a 20 something times difference, right? We'd expect something like a 2 times difference, or 1 times difference, or a 4 times difference, or a 5 times difference. If it's any of those numbers, then we're talking about a failure number much greater than 5. So our expected is that all the different treatments are the same. So we would expect to have in 73 of these non-weight bearing casts for 6 weeks, we expect there to be at least 5 failures if they really were the same likelihood for each of the different treatments. All right, hopefully I explained that okay without tripping over my own words. So that's what we mean by expected. It's not the sample, it's the expected. So just kind of keep that in mind when you're evaluating a situation to see if it satisfies the requirements for our statistics. All right, I'm going to zoom back out a little bit here to make it a little bit easier to read the screen, for me at least to kind of see all stuff kind of together. We're going to use our chi-squared test again. This is a contingency table, so we're not going to goodness of fit. Goodness of fit was our first page, and that was to see if the frequencies are as expected. Here, we're trying to see if there's independence. It's a different type of hypothesis test, chi-squared hypothesis test. So I'll show you where that is in StatCrunch. We do have the null hypothesis, the variables, type of treatment, which is the vertical variable. These are the different types of treatments vertically. And the other variable, which is success or failure. Success or failure are the horizontal ones. So we have these two types of variables, type of treatment and success failure. We want to see the null hypothesis says they're independent, and the alternative is they're not independent. They're dependent, and we want to see if we have enough evidence to refute the null hypothesis in favor of the alternative hypothesis. We're going to perform a hypothesis test with a 0.01 significance level. Okay, and once again, we can do our conclusion based on either the test statistic method or the p-value method. Let's go over to StatCrunch to get some numbers. All right, let me get rid of this thing right here. So I've also typed in the different treatment types and the success and failure. So I've kind of typed all that data from the worksheet I'm showing into StatCrunch. And then I'm going to go to Stat, and I'm going to go to Tables, and you'll see that there's a contingency table right here. We don't have the raw data. We have the summary of these. So we're not showing all 54 successes. We're saying that there were a total of 54 successes. That's called a summary. So we do the summary here. And we want to we have success and failure. So I have to go down to success and failure. Those are my two. I got to hold down the control key if it's going to work for me. There we go. Success and failure are the two different columns. And the row labels are in what's called treatment type. Let me make this a little smaller, I guess, so you can see more. So the treatment type right here is showing all the row labels. So this row here is surgery, etc. So I'm going to go down to treatment type. Again, okay, there we go. Treatment type. There we go. So that's our row label. And then we're using our chi-square test, so you don't have to change anything else. We go to compute, and gives me some information. By the way, it does give you this sort of color-coded chart, which is nice if you want, but you don't really need to use it for our purposes. We just need the sort of readout for this particular test. And this was the totals for all the different rows and columns of the contingency table. We have our chi-squared test statistic. We have 3 degrees of freedom. Oh, degrees of freedom. In case you're wondering how we got degrees of freedom, the number of treatment types is 4. So n-1 would be 3, right? That's not why this is a 3 exactly. But do notice that 4 minus 1 is 3. On the horizontal variable, we have 2 of these, success and failure. So if we were looking at n-1 for this categorical variable, 2 minus 1 is 1. So we have 4 minus 1, which is 3, and 2 minus 1, which is 1. And the way you find degrees of freedom is you multiply those two numbers together. So we got 3 times 1 is 3. I'll show you that on the worksheet as well, but I can't write on this using my pen. We have our p-value and our test statistic right here, value of 58. So I already typed those numbers into the worksheet here, which is over here. And we can look up the same critical value using the degrees of freedom and the 0.01. I'm not sure it's going to let me do it again. Yeah, it just keeps jumping around. Let's see, go to this one here. Yeah, here, I can get the test this way. And we had 3 degrees of freedom. We have a 1% significance level. So 1, 2, 3, we get 11.345 at the 1% level with 3 degrees of freedom. So hopefully I type that number in over here. Test statistic 58.39. Maybe that's a typo. Oh, 58.39 was the number I got over here. that's the test statistic over there. What I should be comparing it to is the critical value of 9.21. Let's see if that matches up. Here's the 9.21 right here. So it looks like I did maybe write down wrong because that's only 2 degrees of freedom. 1, 2, 1, 2. Yeah, 2 degrees of freedom is 9.210. Ours is supposed to be 11.345. So let me fix it up real quick. In this case, it doesn't make a difference for our conclusion, luckily, but it does look like I read off the second row instead of the third one. And once again, to get degrees of freedom, I'll show you up here. We have 4 minus 1 degrees of freedom. And over here, we have 2 minus 1 is our degrees of freedom. So on the horizontal, we have 1 degree freedom. On the vertical, we have 3 rows of freedom. And then we have our table degrees. So the degrees of freedom for the whole table, we would just multiply the 2 degrees of freedom together, and we would get 3. So that's the table degrees of freedom. And unfortunately, I only went down 2 when I was, pre-doing the calculations, but I found my mistake and I fixed it. So going down 3 spaces, you get a critical value of 11.345 according to that table thing there. Whether it was the 9 that I misread before or the 11 that I got this time, you'll notice that the critical value is indeed smaller than the test statistic. So we do have enough evidence to reject the null hypothesis. And for the p-value method, we should also have enough evidence. The p-value was, it was like basically 0. It's less than 0.00001. So that's our p-value. And that p-value is basically 0. So it's definitely going to be less than the significance level of 0.01. So again, using either method, we get the same conclusion that we can reject the null hypothesis. We have enough evidence to reject the null hypothesis. So we're rejecting the claim that the variables are independent, which means that the relationship between the type of treatment and whether or not the treatment is a success or a failure is a dependent relationship. There is a relationship between those two, which is good. So then you can try to find like the more likely treatment to have success, and whether that's within, I guess, financial possibilities, or whether the clinic you're at does that type of treatment. But you can kind of use that with the knowledge that it really does depend on the type of treatment used. Okay, so hopefully that explained these two learning objectives. Once again, we wanted to determine whether we can refute a given claim of expected frequencies. We used a goodness of fit chi-square test to do that. And the second thing was we wanted to determine whether the 2 categorical variables in a contingency table are independent. And we just use a contingency table independent test of independence to do that. If you have any questions or want to go over these problems or have any what if scenarios, please don't hesitate to reach out to me either by visiting my Zoom hours or by emailing me. I hope you have a very enjoyable day. And good luck on the upcoming exams for this class and anything else you're working on. All right. I will see you hopefully sometime soon.